Now we're thinking about the chemical force first, and we're considering both ions. So for our chemical force, sodium, greater concentration outside, potassium, greater concentration inside. So the chemical driving force for sodium is into the cell, and for potassium, it's out of the cell. Okay, so that part is pretty straightforward. The chemical force on both of our ions, in other words, the concentration gradient for both. Now, when we think about the electrical force, so bringing into the picture the permeability is important because, as we mentioned earlier, potassium has more channels, right? The cell is more permeable to potassium's movement than it is to sodium. So in actuality, while we say that the electrical force, okay, but while we say that the chemical force is going to be moving our ions in different directions, we now need to think about the permeability. Potassium is going to have more opportunities, more doors, if you will, to leave the cell because it has a greater permeability. So as potassium leaves, now there becomes a negative environment inside the cell. So this is the difference that I mentioned earlier between our hypothetical cell and the real scenario when we bring both of our ions into the question. Also, when we consider the permeability, the fact that potassium has more doors, more channels to move through the membrane than sodium does. So as these two ions begin to move according to their concentration gradient, we're going to see that potassium leaves more than sodium enters. So now we have a negative environment on the inside of our cell, and now we have a positive environment outside. And now we can begin to think about the realistic electrical force that is acting on both of the particles. Okay, so now we've established a negative environment inside of our cell. We're going to look at potassium's movement. Potassium's electrical force will want to move it into the cell because potassium is positive, the inside of the cell is negative, right? Opposites are attracted. Now, the same will be true for sodium. So for sodium, the positive charge will be attracted to the inside of the cell, which is now negative. So again, notice the difference between a hypothetical cell only permeable to sodium versus a cell where we're considering the permeability of both sodium and potassium, right? The realistic scenario, which means that sodium's forces are both acting to move it inside of the cell. The chemical force moving it inside according to the concentration gradient, and the electrical force moving it inside according to the realistic negative environment because of the greater permeability to potassium. Okay. Now, if we think about the magnitude or the speed or the sort of the flow of these ions, because potassium has a strong force outward and a smaller force inward, it's going to have a weak movement out of the cell because we have to subtract that weaker force from the stronger force. So the overall direction is out of the cell, but the magnitude of that is going to be quite weak because we had to subtract the smaller electrical force. For sodium, it's going to be simply combining those two values, and the overall direction will be in that same general direction. So both forces are acting inside of the cell, and so we add those two magnitudes together, and so now we have a strong force, right? A strong current that is pushing sodium into the cell. So in summary, potassium is leaving the force by a weak force, kind of trickling out of the cell. And sodium is entering the cell by a strong inward force, really rushing or flowing into the cell. Okay, so potassium outward is slow, and then sodium's inflow is fast. So as we think about that movement happening in conjunction with the sodium-potassium pump, so now we have potassium trickling out of the cell, according to both of its forces, both electrical and chemical. But there is the sodium-potassium pump that is pumping potassium back into the cell. So we have the leaking of potassium out and the pumping of potassium in. So eventually, those two mechanisms are going to arise at a steady state. The same is true for sodium. We have a strong rush of sodium into the cell, and then we have three sodiums being pumped out of the cell by the sodium potassium pump. So again, both of those movements, the inward movement and the outward movement, are going to arise at a steady state where there's no longer any net movement. There's no longer any net flux of ions in one direction or the other. The inward current is exactly balanced out by the outward flow in the opposite direction. Okay, and this is what we mentioned earlier as the pump leak system. The sodium potassium pump pumping ions in one direction, and these leak channels facilitating the ionic movement passively in the opposite direction. And eventually we arise at our negative 70 millivolts. Okay, so that is how we establish the resting membrane potential by thinking about our sodium potassium pump and the relative channels, and then the chemical and electrical driving force that are acting on each. Okay. All right. So just to kind of reiterate that here again, here's our sodium potassium pump. It is going to pump 3 sodiums out. As we pump more sodium out, we have the leak channel for sodium, and the proportion here is drawn to show that there is 1 sodium and there are 3 potassium channels or doors, right? Now, what that is reflecting is that there is a greater permeability for potassium than there is for sodium. So more potassium leaves by way of the sodium potassium pump, and then it's going to rush in through fewer channels. It's going to rush in because it has a stronger force, but it's going to do so through fewer channels. So that essentially balances out the movement of sodium. All right. Now for potassium, the opposite is true. We have the sodium potassium pump moving 2 potassiums in, so fewer potassium, but now potassium is going to trickle out of the cell, but it's going to do so through more channels, 25 times more so than sodium has channels to move. So there's going to be a weak force for sodium leaving the cell, but many more passageways or channels to do so. And eventually, that pump leak system gets to a balance where there's no longer any net movement of potassium or sodium. And then at that time, if we were to, again, put a voltmeter into our neuron, the resting value would be negative 70 millivolts, favoring an abundance of negative charge on the inside of the neuron. Now we can begin to kind of look at this in different ways from different perspectives and think about the equilibrium potential for both of our ions and how those two numbers, excuse me, compares to the resting membrane potential. So sodium has an equilibrium potential of positive 60 millivolts, which is one, first of all, it's more positive, right? Second of all, it's really far away from the resting membrane potential. And what this reflects is the fact that sodium is not only moving in a strong inward current. So because sodium needs to move into the cell, right? When sodium is at equilibrium, the inside of the cell is really positively charged. Okay, when sodium is no longer moving, when it's at equilibrium, the membrane potential at that time favors excess sodium inside the cell as a result of that strong inward current. What this also tells us is the force with which sodium wants to move. So when the cell is at rest, sodium is really far away from its comfort zone. So that is also a reflection of the force, right? That sort of the magnitude with which sodium wants to move. Okay, the distance it is away from its equilibrium state. Now let's think about potassium. Potassium is fairly close to the resting membrane potential. It is also more negative, right, which is similar to the resting membrane potential. So what this tells us is that sodium or potassium's movement is very weak because potassium is really at home, it's close to its home, it's close to its equilibrium when the cell is at rest. So the strength with which potassium wants to move is much weaker than the strength with which sodium would want to move. Because at rest, potassium's movement is going to be closer to its own equilibrium. Now, what this also tells us is that potassium moves in the opposite direction. So because potassium is leaving the cell and it's positively charged, when potassium gets to its equilibrium state, there's going to be a negative environment inside the cell as potassium has left the cell. So the equilibrium potentials for both of our ions, again, these are fixed values, these are never changing. When we look at how they compare to the resting membrane potential, this really begins to tell us a story of the force acting on these ions when the cell is at rest. Okay. Now, if we think about the membrane potential, so if the membrane potential in a neuron is not at equilibrium, then the electrochemical force is not going to be zero. In other words, there's going to be movement of the ions in whatever direction favors the ion getting closer to its equilibrium potential. Okay, I can't speak today. So another way to express that, another way to say that, ions move to get closer to their equilibrium. So another example, when the cell is at rest, potassium is going to be moving inward. It's going to be rushing inward because it wants to arrive at its equilibrium potential, which is very, very positive at positive 60. Same for potassium. When the cell is at rest, potassium is going to want to move to arrive at its equilibrium potential. So if the membrane potential is not at the equilibrium potential for an ion, then there's going to be movement and the electrical force will not be zero. Okay. So the net force acts to move the ion in a direction that is going to favor it becoming at equilibrium. So for potassium, that will be outside of the cell, right? The net force acting on potassium moves it out of the cell because moving it out of the cell helps to bring it closer to its equilibrium potential, which is more negative than the resting membrane potential at negative 94. And for sodium, sodium wants to rush into the cell because at positive 60, there needs to be more positive charge inside the cell. So sodium is going to move in the direction that will favor it arriving at that positive 60, which is its equilibrium potential. The strength of the net force. So this is the direction of the force. That is going to be dictated by whether or not the equilibrium potential is positive or negative. The strength of the force is dictated by the distance away with which the equilibrium potential is from the membrane potential. So for sodium, it's really far away when the membrane potential is negative 70 and the cell is at rest. Potassium is really uncomfortable. It's really far away from its equilibrium potential. So that is going to dictate the strength with which, I keep saying potassium, I'm sorry. Sodium is really far away because it's at positive 60. That is where it wants to be, but the cell is now at negative 70. So sodium really wants to move into the cell to get closer to its equilibrium potential. And then for potassium, potassium is fairly close to the membrane potential at rest. And so there's going to be a weaker force moving potassium in order to get closer to that negative 94. Now, we're just going to keep reiterating this. This is a concept that takes a lot of repetition in different ways, from different perspectives, just to make it stick. So we're going to go over this in just a slightly different perspective here. So our resting membrane potential value is negative 70 millivolts. Oops. So our negative 70 millivolts. Potassium's equilibrium potential is negative 94 millivolts. So the membrane potential here, when the cell is at rest, is 24 millivolts less negative than potassium's equilibrium potential. And what does that mean? First of all, it means that the electrical force is into the cell and the chemical force is out of the cell. The chemical force is stronger. So we subtracted that weaker electrical force, and now we have this much smaller value of 24. So the net force moving potassium is out of the cell, but because there are more potassium channels, or there's a higher permeability, there's going to be an outward flow that is balanced and moving it out of the cell. If we think about sodium on the other end, sodium has an equilibrium potential of positive 60 millivolts. That means that when the cell is at rest at negative 70, this is 130 millivolts less negative than sodium's equilibrium potential. So now we have a much stronger magnitude. So this number here, just combining these two values, gives us the absolute value, which is 130, and the overall direction is in the direction of both forces, right, into the cell. So now we have a strong force moving sodium into the cell, but we have fewer channels, or we have a lower permeability for sodium. Okay. So here's our small force for sodium, leaking it into the cell because we have fewer channels, lower permeability. Our force for potassium, moving it out of the cell through more channels, so that's a higher permeability. And then we have the sodium-potassium pump just balancing those movements out and establishing the negative 70 at rest. Now, the importance of establishing that negative 70 is now we can begin to think about an action potential. So because we are at negative 70 at rest, now we can excite the cell. And the way that we're going to excite our cell and bring about an action potential is by opening up more channels. So now we're going to move away from thinking about our leak channels. So our leak channels dictate the state of the cell when it's at rest. And now we're going to consider our ligand and our voltage gated channels. So these channels are going to be gated depending on a certain criteria, whether that be a change in the membrane potential or something binding to this channel. And now we can think about opening up additional channels and having additional ionic movement. And that is the basis for which we can excite a cell or generate an action potential. And the action potential is extremely important. This is one of the major ways that we communicate. So the way that you excite muscles, for example, cardiac muscle, smooth muscle, skeletal muscle, is by firing an action potential on a neuron. And then that will be a communication or a chemical signal that will instruct the muscle to contract. So the action potential is a means of communication between our neurons and many other cell types, muscle cells, gland cells, etc. So thinking about the resting state is really the basis for us to begin to think about how can we excite these cells and stimulate this action potential.